we'll start you off with a little experiment about ellipses. All you're going to need is a piece of paper, a couple thumbtacks, and a piece of string, but you can tie the string in a loop. All right. So before we get into proving or doing anything with the ellipses, I'm just going to kind of show you a little trick of how you generate one. So what I'm doing is I'm putting string on these two thumbtacks, and these 2 points are going to be called the foci. We're going to get into how you calculate all that eventually. But they're really similar to a parabola. There's a lot of similarities between a parabola and an ellipse. In fact, an ellipse is almost like two parabolas that kind of face one another. So all you got to do is just take a pen, pencil, marker, whatever, and just kind of go as far as that string will allow you to go. And just kind of carefully go along there. And it's going to etch out a nice, perfect little oval shape or an ellipse. Okay. So some things you'll start to talk about today. Major axis is the distance all the way across here. So kind of note this. If I stretch this out as far as it'll go, the length of this string is the major axis. And really, to get into the definition of how this works, we'll get into it in just a moment. Anywhere I go, this length plus this length has to still be this length all the way across here that we're calling the major axis. So no matter where I go, those totals are the same, and I'm going to demonstrate that in Desmos next. So one more preliminary item before we get into what an ellipse actually is. You've probably heard me mention conic sections. You've probably seen the title in the book at this point. So I'm going to start using it officially now. Conic section, all these shapes we're doing so far, they come from taking a cone and cutting in different directions, cut in different ways. So first up, we'll talk about a circle, and that one's probably pretty straightforward because you know a cone is like a triangle crossed with a circle, depending on which direction you look at it. So if I cut this cone just straight through, I guess a way to define that, if there was a axis kind of straight through it and we cut perpendicular to that, we would get a circle. Okay. If you were to cut through this thing anywhere that's not perpendicular, and it probably kind of makes sense why a circle and an ellipse are very similar. If you cut through this thing at more of an angle to the axis, you would get an ellipse. Okay. So there's that. And if you just come straight down into the cone, any angle really, just as long as you don't cut all the way through it. So really, to define that, if this is a slope, it's got to be cut slightly less than the slope through. Otherwise, it would cut all the way through the cone, make an ellipse. But if you cut into the cone, you get a parabola. If you cut straight in that way. Okay. And there's still one more shape, and we'll talk about that in the next lesson. All right, let's formalize what an ellipse is. So it is an oval shape, that's true. The key things you got going on, you've got these two foci, and it really is similar to two parabolas kind of facing one another. And some of the reflective properties of the parabola also work with an ellipse. So a lot of those things are the same. The key thing that we just did with the string, if you pick any point on the ellipse, this distance plus this distance, the distance to each focus, has to equal the same as the, effectively a diameter, the major axis, what we call that, the large diameter. Because if you think about diameters, this would have a biggest possible diameter and a smallest possible diameter. And then if you kind of cut through, you'd have everything in between. So another Desmos demonstration. Again, every section here has some Desmos demonstration if you want to check them out. So here's the one on ellipses. And what I've done here is just to illustrate that this distance plus this distance is the same as this major axis. So can't remember why I colored it different, but here's the red distance right here, the green distance right here, just to show the two together. And I don't know why I did the orange and black, two different colors, but just to show you that this is the major axis. And you can play around with center point, of course. We haven't defined what A and B do quite yet, but you can see you can play around with those, and everything stays proportional. This will stay the same length as those as the major axis. You can make this thing a little taller. You can make it more narrow, and you can see how that effectively changes these two distances. But the thing I really want to show you, and I've got a slider here that says slide P to move the point. All these things I tried to put directions kind of in these little quotation mark spaces. So if I want to slide that point around, you can see that no matter where I go, these two distances still add up to the same thing as that major axis. So just to prove that point, It's guaranteed, always true. I'm actually not going to, this is as close as I'm going to get to a proof. I tried doing the proof just to see how I want to go about showing that to you. And it's pretty elaborate. Again, it's pretty similar to a parabola, same setup. You start by saying this distance plus this one plus this distance is equal to 2a. So I haven't quite told you what a is, but a is from the center to the edge, kind of like a large radius. So 2a would be that major axis, like the large diameter. And I put the points right there on purpose because the distance from here to there, plus from here to there, which is the same as this, would equal the same as that major axis. That's kind of where you would start to prove this. So anyway, that's how that would go. So rather than prove this thing, I'm going to just kind of jump right in and graph one. So here's the standard form you're going to see. I'll give you the equation in just a moment after we run through where all the pieces go. And it's actually pretty easy to graph one of these things, so I think it's just best to start there. Then I'll point out some similarities to circles, and then ultimately I'll show you how to, not derive, but just how to get the formula, where all the pieces go, and what the variables are called in the formula. So something similar, we've got this, here's our HK, which is going to be the center point. You've been seeing x plus or x minus your center point, y minus your center point squared. So that will be the same throughout the whole chapter. So this will be -1, +4 for your center point. So pretty similar to what you've been seeing so far. So -1, +4. Now, these numbers underneath, and it's always going to be equal to 1. These are some things we'll point out. This number underneath, these are going to act sort of like radii. With a circle, you had to take the square root of the number over here, which is the radius. These are like two separate radii in the x direction and the y direction. You take the square root of those just like you did for the radius of a circle, so pretty similar there. So for 16 being here, I'm going to go ahead and tell you this is called a squared. So a would be 4. And that's how far we're going to go in the x direction, left to right. So we'll go over to 3, we'll go over to -5. Now the y direction, this one's going to be called b squared. So b would be 3. Take square root of 9, you get 3. That's how much you're going to go up and down in the y direction. So up 3 here, down 3 here. Once you've got the center and 4 points, that's really what I would use to freehand these. And let's see what I can do. Never know how it's going to turn out. That one wasn't too bad. So again, there's our ellipse drawn out. That's how you take the equation and turn it into a graph. It's pretty straightforward, not too bad. So let me compare this to a circle, and then we'll get into definitions. So similarities to a circle. This is really similar to the example I just did, except I made it 16 on the bottom of both of these. So center point, same place as that ellipse we just did, -1, 4. And if these weren't there, or actually if the 16 was over there, it would look just like a circle. So this would mean go 4 left and right, go 4 up and down, so 8, 0. That means go over just a little more, there we go. Now it's a 4. And there we go, we'll fill that in, make a circle out. Yeah, not the best circle, I know. But watch what happens if I take the equation. And it's an equation, so I can do whatever I want as long as I do it to both sides. Multiply both sides by 16. And if we do that, we're going to get x, well, the 16s go away on these denominators over here. So x plus 1 squared plus y minus 4 squared equals 16 on that side. So there's the definition of a circle. Really, all you're doing for an ellipse is you're getting it equal to 1, which means you're dividing by whatever this radius is over here on both parts on this side. And what you're going to find with the ellipse, when you do completing the squares, they're going to have leading coefficients out here that are different. Those leading coefficients are going to change the distance you go up, down, left, and right. And that's why it's longer in one direction than the other. And they can be oriented like tall and kind of narrow this way. So you can see them oriented kind of taller or wider. Those are things you'll see. Eventually, in higher levels of math, you can see them oriented slanted. So that's something else that will happen eventually. Not in this chapter, but later in higher levels of math. All right, so let's formalize some points on the ellipse, and let's nail down an actual equation and define where things go on the equation. I'm going to come up with some more names that you're going to be asked about in the book, some important properties here. So HK is continuing to be our center point, as always. XY is any point that lies on the ellipse itself. When you get down to it, the only thing that really shows up is the edge of this thing, which makes the oval shape. Everything else is just kind of helper lines and things we put in there to help us visualize what's going on and do the math. But really, in the end, all it's here is these XY coordinates that make up the ellipse itself. So HK is the center point. We've got A, B, and C now. And this will carry through to the next shape we do in the next section. You'll have A, B, and C. A is how far you go from the center to the furthest point out. So it's like a large radius. And we've already talked about how that's called the major axis, which is like the longest diameter you can have for your ellipse. And that radius, if you will, for the major axis is called A. That's from the center point to the furthest edge open. From the center point to the smallest place away, like the smallest radius, we call that B. So here's length B right here. I put it on the outside so it's a little bit easier to keep this less cluttered anyway. But from there to there is length B. This is called the minor axis if you go all the way across. So you'll see that term. B is like the minor radius, I guess you could say. C is the focal distance from the center point to the focus. A little bit different than parabolas. Parabolas, you went from the vertex to the focus. Mathematically, you'll see it just makes more sense to start from the center and go to the focus, the way ellipses are constructed. So really, that's the only reason we don't. You certainly could make a definition that goes from the edge to C like this, kind of like for a parabola. It'd be way more involving, so we just don't want to do it that way. Your equation is going to begin just like any other equation we've done so far. It's x minus h squared plus y minus k squared. That's your center point, just like for a circle. Instead of being equal to a certain radius, these are always going to be equal to 1. A lot of times you'll have a number over here like a radius, but you'll need to divide by that over here, or divide by it on both sides, so that's equal to 1. And that just makes it really easy to see what these lengths underneath the x and y are going to be that act like your radii. And really all there is to it now, you're going to have whatever, and I'm only going to do it this way because this one's oriented longer than it is tall. So the a value goes underneath the x term, and it's a squared, whatever this distance is here squared. And then whatever the distance is from here to here squared, so that's b. If this thing was oriented more tall, then we would put the a underneath y. A is the longer one, B is the shorter one. That's really that's the only thing that matters. That will matter when you get into defining the focus. That's why I'm making a distinction there. But really, that's how you decide which one you call A and which one you call B. The bigger ones you always call A. All right. The definition for C is going to involve some subtracting, and it's going to involve taking a square root. So if you took the square root of a negative, it would say that the focus couldn't exist, but it can. So that's why it's that's why you got to make sure the biggest one is A. Here are the terms we need to define. We need to define them in terms of these variables that I've presented to you. Now, you probably don't need to sit here and go through all this process or memorize all these, but I'm defining them just in case you need to look back and kind of see how things are playing out. So the center point, as always with everything in this chapter, it's HK. Okay. The major axis, well, that's going to be 2A. Major or minor axis is 2B. If you think of A as being like a radius, then twice that radius is a diameter, the distance all the way across. Same thing for B. If that small radius was B, then all the way across would be 2B. Okay, vertices, you just take your H for your center point, and plus or minus your A value. That's if it's oriented sideways. If it was oriented more tall, then you would add your B value. This probably makes it more complicated thinking in definitions, but I'm just going to put them up here. And for the Y values, you take K plus or minus that B value. Again, that probably makes more sense just looking at it. Take your center point, add this distance here, subtract this distance this way. For the y direction, add this distance, subtract this one. So that's really all I'm saying with that. The one thing I do want to derive with you all is the focus, and it's not too bad to do. So a couple places to think about. I'm going to put a point right here on the edge of the major axis. And we talked about this a little bit, but these two lengths from each focus to that point, if I put it right there on the edge, it is equal to that major axis, which we said is 2 times A. So we'll flash back to here, and this is a statement that this has got to be true because of that. The two distances added together have to equal this entire distance across here. So again, that distance plus this one has to equal this distance all the way across. That's what I just showed you from that Desmos. So a good way to figure out what these distances are is to put the point right here. We're just putting it in specific places that make these easy to figure out. So I'm putting it, if I can land it right on it there, well, close enough. So if I get right up there, imagine it's right above that point, then that's going to make this calculation a little bit easier, because if this is C from here to here, then this length right here is purely C, and from here up to this point is purely B. That makes this way easier to do. So I'm going to come back here, and that's what I've got going on. If this XY coordinate is directly above here, and you could do this from any position. This is just the easiest one to calculate it for. So this length has to be C from the center to the focus. This length has to be B from center to the top of the minor radius, if you will. Before I do anything else, these distances are the same. So I'm going to go ahead and say that added together, they're just 2D, if you're okay with that. And so that means D has to equal A. Okay. So at this particular point, this distance has to equal that length right there. We don't need to really stretch it out to show that. The algebra is showing it, so let's continue on from that stage. So that means this distance would be, through distance formula, square root of this p squared plus this one squared. So square root of b squared plus c squared is a. Okay. Again, that distance, if you do Pythagorean theorem, this squared equals this squared plus this squared. So the distance itself is square root of these two parts. All right. Now I want to go ahead and square it. Square both sides to get rid of that square root. And if I'm trying to define c, which is my focal length, that's what I was trying to derive, then c squared is a squared minus b squared. And ultimately c, the focal length, is square root a squared minus b squared. Sometimes you can get by going just with c squared, depending on which situation you're in, but there it is fully taken to c. This is why it's so important that the longest major axis is called A. Because if it's not, then this becomes an impossible situation. If A was the smaller one, now we're taking the square root of a negative, and that says the focal length doesn't exist, but we can actually show a contradiction, show that it does. So anyway, just to make things simple, A is always the biggest one. So here's how I'm going to handle the focus. I'm going to say it's H plus or minus C, and then K. Now if this thing was oriented more vertically, you would add C, or plus or minus C to the K value, and everything would be on the same X coordinate, so H would be the same. All right. But to get C, let me just put that little note down here. A little star next to it. C is square root a squared minus b squared. So if you're trying to find, if you've got C, great. You just add it to your vertex or your center point. If you don't have C, you got to use a squared b squared to find it. Usually at this stage, most students are feeling a little overwhelmed by all the stuff I just threw at you, but now once you run through an example, usually it kind of falls into place and you see it's not really as crazy as it might have seemed like it was. Some of these definitions for conics actually, to me, make them more complicated than just doing the problem. So let's just jump in here. Center point's going to be at -2, +4. So let's get that on our graph. -2, +4. All right. I'm going to go out 5 in the x direction, left and right. So here to 3, back to -7. I'm going to go 2 up and down on the y-axis. So right there and right there. All right, I'm gonna cheat, so I've got a nice example. It looks good for y'all, but of course on paper you want to draw it by, just kind of connect the dots, draw by hand. All right, let's see what we can find out here. We need to get the vertices. So the vertices are, and I'm starting with these because they're usually fairly easy to come by. So our center point we said was at -2, 4. So -2, 4. And I'm just going to label these on the graph itself. I think that's just easier, but on paper you want to list them out. So it looks like 3, 4 is going to be our vertex right there. On this side it's going to be -7, 4. And we went up and down from that center point, so -2, 6. And -2, 2. So those are my 4 vertices. Now this is a case where I don't have C given to me. I've got to figure it out. So C is, again, square root of A squared minus B squared. So in this case, it's going to be square root of 25 minus 4. So square root of 21. Okay. And I probably should have put plus or minus, although we're going to go plus or minus, so I guess it really doesn't matter here. From this point, from -2, you're going to go over square root of 21, and you're going to subtract a 2. So let's try to make that as straightforward as I can. Now square root of 21, that is bigger than 4, smaller than 5. So I'm going to try to make it look according. That's going to be somewhere over here, somewhere over here. And again, I'm just going to label this on the graph. So -2 plus square root of 21, with 4 still being the y-coordinate for your vertex. And the other focus, it'll be -2 minus square root of 21, and then still 4 for that y-coordinate. We have one final term to talk about, and then we're going to do an example of completing the square. Last term is eccentricity, and it's a measure of how oval the ellipse is on a scale of circle to line. We'll get into more specifics from that. So the way you do it is just a ratio of C to A. So just flashing back to Desmos here. If this is C and this is A, again, it's just a ratio of C divided by A. That's all it is to find your eccentricity. So let's play around with some things that could happen. I'm going to try to get A and B to be really close to each other, which should make this thing start to look more circular. And watch where the focus is going to go as that happens. So it's going to start to get more circular looking. And A is coming in, but C is coming in faster and getting closer to the center point. If I can land it right there at 3, then now my focus is the center point. And that would be a case where there is no distance from the center to the focus, so it's 0. By definition, your eccentricity would be 0. This is not eccentric whatsoever because it's a circle. So it's like a measure of how skewed the circle is. If you go the other direction here, start to spread this back out, the wider it gets compared to how tall it is, the further out C is, or the closer C is to your vertices. So I'm going to take it as far as I've got my parameters set here. And I'm going to squash it down a little bit just to kind of see how that plays out. So again, the wider, or the longer it is on the major axis compared to how big the minor axis is, determines how far out C is, how close it is to the vertices. Now you can take it all the way. I'm getting pretty close now to where they're almost the same. And eventually, and we could play with all the math here, but I think the visual's good enough. If I shrink down B enough, well, it probably isn't too hard to think about that. If B was 0, well, it would be divided by 0, so that's kind of an error. Maybe right up to that point, the amount I'm going up or down is getting close to nothing. So this thing essentially becomes a line at that point. So a line is about as eccentric as a circle can get. It's completely squashed down. So that's kind of that's the way it goes. At that point, your C value would be the same as A. So you would have a eccentricity of 1. That's not possible for an ellipse, And that's kind of where the math breaks down because it's no longer an ellipse, it's a line. So right up to the point before everything breaks down, it's almost a line. So you'd be 1 for eccentricity. So it's on a scale of 0 to 1, how eccentricity. So basically it's a scale from 0 to 1, it's how eccentric you are. Like a percent almost. That's really a good way to think about it. It's like a percent. So let me uncover these details. So it's on a scale of 0 to 1. 0 is a circle, 1's a line. If some of the math stuff was hard to remember, this is easy. 0 looks like a circle. 1 looks like a line. So that's, if it looks like a circle, it's 0. If it looks like a line, 1. And the more stretched out it is, closer it is to 1. More circular, closer to 0. So again, the way you get it is divide C by A, once you've got those two values. So let's this will be a sort of final example that wraps everything up. Given your equation, we're going to graph it, we're going to find the eccentricity, and we're going to have to complete the square to get there. So this kind of completes all the skills you're going to need for this section. All right, well first up, I want to group my x's together. So 4x squared minus 8x. For now, I'm going to go ahead and just kind of leave those like they are. Next is y squared plus 4y. And I'm going to go ahead and add 8 to both sides so it's out of the way there. So there's all my terms. Everything's good. These are grouped. These are grouped. Anytime, when you complete the square, anytime you have a number in front of the x squared term, you have to factor that out no matter what it is and no matter how inconvenient. Now this time, this is a common factor, but even if it's not a common factor, if this was a 7 and this was a 4, you got to factor 4 out and you got to roll with that fraction it creates. So 4x squared minus 2x, leaving a space to complete the square there. Fortunately for y, I don't have to worry about completing or pulling anything out. I do have to complete the square. So I'll leave a little space to make that happen. And I'll try to color code this. So ignore the 4 for this completing the square part. Take half of this term, which is 1, square it, so plus 1. Now, I created a 1 here, but really I created a 4 on this side of the equation, so I've got to add 4 over here. Half of 4 is 2, square it, you get 4. Nothing in front, so I created a 4 here, I've got to create a 4 on that side to balance it out. And that gets us to this point. So I'm going to do a few things together. I'm going to leave 4 up front. Go ahead and make that a perfect square trinomial. Or make the perfect square trinomial a perfect square binomial. Y plus 2 squared here. And that's going to equal 16. The final step on these is you've got to get them equal to 1 to get the proper format. So to wrap this up, it's going to the 4 and the 16 reduce to 1 over 4. So x minus 1 squared over 4 when those reduce out, plus y plus 2 squared over 16 equals 1. Because this is just, think of that as being 1 over 16, so it doesn't really reduce. I do want to write them separately. Makes it a little bit easier to do get the graph. And that should do it. Now I purposely picked one finally here for you to have oriented vertically, so you kind of see how that stuff plays out. All right, so 1, negative 2, that's going to be the vertex, or sorry, center point, not vertex. All right, I'm going to go 2 left and right. That's the minor axis this time, that's the b value. And I'm going to go 4 up and down, because that's 16 underneath the y. All right, so this time the major axis is in the y direction. So there's the ellipse graph. We are supposed to find eccentricity. So just a general reminder, since it's a new term, that is the ratio of C to A. Now C is probably going to be somewhere in here, but we can find exactly where it's going to be. C is the square root of A squared minus B squared. A's got to be the bigger one, so 16 minus 4. C is going to be the square root of 12, and if you reduce that down, you're going to get 2 square root of 3. 2 square root of 3, so that is, or just think about your square root of 12 is bigger than 3, smaller than 4. So if you want to put the focus on the graph, it's about right in there. You go a little past 3 down as well. So about right in there. So this is fairly eccentric, because when I get E, I'm expected to be pretty close to 1, just looking at where the focus is. So let's go ahead and wrap that part up. So eccentricity is C divided by A. So 2 square root of 3, my a value, well, a squared is 16. So my a value is 4 here. So we'll put 4 on the bottom, reduce, square root of 3 over 2. And this is one that's off the unit circle. No real relation here, just that we know that we're familiar with that decimal number. It's about 0.86, 0.87, so pretty close to 1. Seems to be lining up with what I'm expecting to see. Just sort of final little fun note. If you've ever messed with the orbits of the planets and know a little bit about those, they are ellipses, even though they kind of look circular. Eccentricity, they're pretty close to 0. So the sun is at one focus of the ellipse, and there's sort of an imaginary theoretical focus at another point. But just something to kind of play around with to see. The plane of the solar system, the equator of the sun, we kind of loop around that a little bit. And this is just a picture that's, somebody took a picture, I think, every 3 days or something throughout the year. Same time every single day. Of course, the sun's going to be higher and lower in the sky depending on the season. And you just kind of see how that plays out and how we sort of loop around that, how our orbit is, and how our orbit's a little bit closer. We're a little bit closer to the sun one time of the year than the other. We're actually closer in the winter than we are in the summer here in the northern hemisphere. And then you got to focus over on this side. So a few little things you can kind of take away from that. It's just kind of neat to see.